All right, thank you. Yeah, I'm Philart. Before we dive into the presentation, I'm from South Korea. I got my degree there, first master's in cognitive science, and also studied film scoring. Worked in a couple of companies like Daum Communications is a Korean version of Google, and LG Electronics. Then moved to Georgia Tech. I got my PhD there in engineering psychology and HCI, and moved up to North. So I worked at Michigan Tech 6 years. I got my early tenure there, and in 2018 I came back to South. So I'm here at Virginia Tech. All right, so my lab is called Mind Musing Machine Lab. We do research on HCI or HRI with focus on human emotions and sound. So why I'm interested in these two aspects, because I wanted to see holistic approach when we do this HCI, because traditionally they really focused on cognitive information processing. That's why we wanted to add emotions and affect to HCI. And also traditional HCI really focuses on GUI, graphic user interface. So we do music and sound and auditory display, but also all kinds of other multimodal displays. And with these two themes, emotion and sound, I have three different research application domain, driving, assisted robotics, and arts and extended reality. So today, I'm going to talk about three research pillars, some representative projects in each pillar, after I go through the aesthetic computing concept first. So when you hear about art, what do you think about it? Some people define the art as a evolutionary product, and some people say, "Oh, that's just cognitive processes." But somebody like Ellen Disanayak, she's a aesthetics researcher, defines the art as making special. So we all love making special, right? In our life. When you're 2 years old or 3 years old, think about it. You were painter, right? Drawer, drawing something. You were dancer, right? And you all forgot about that. So people just, forgot at some point they were, making something special, right? So I want to make it revive that momentum again, so we can all, making special in our everyday life. So another word I can tell you is arts, and that's origin of craft, technique, and science. So we do science and engineering, and arts is the word. And as you see here, art and arts, oh, it's kind of very similar, right? Yes. So uh, the word, the origin of two words actually from the same. So if you see the history, some artists, they really wanted to use technology like futurist or fluxus movement. They wanted to reintegrate, right, the arts and technology into one. And I think in 2025, right now in this era, I think this is really high time we can see the opportunity to reintegrate art and technology for everyone. So you can be again, artist and dancer. So that is what aesthetic computing wanted to do. So they define aesthetic computing as the application of art theory and practice to computing. So when I say art theory and practice, you might think, or it might be curious about what do you mean by art theory and practice? I mean by that, really, what we call art in our everyday life. So theater play, dance, music making, or painting. So you will see in my lab, we do all kinds of these artistic activities uh, all together. So you probably can think of the influence of technology or computing into art and aesthetics. So think about camera, right? It's technology, or cinema, right? Film. That's really based on technology. So we see a lot of this direction from technology to art and aesthetics. But then can we think about the other way around? So can art and aesthetics influence technology and computing? So that's where aesthetic computing started. So where that want to intervene. To me, so I can define this as a computing, the reciprocal interactions. So as the tradition, right? So computing and technologies can influence art and aesthetics by expanding perceptual dimensions, right? Think about VR and AR, right? So we can have new experiences. But also, art and aesthetics can influence computing by expanding representations of computing process and structure. So that's I see what aesthetic computing can do. Then why I'm interested in this aesthetic computing? We have some benefits. So we can explore more creative and innovative media, and we can make computing more accessible for everyone. And so we can promote personalization and customization of computing structures. All right, so that's the premise of aesthetic computing, the today's presentation. Then I'll go on three different research pillars: driving, robot, and art. So the first one is about driving. Like I said, all HCI or driving research really has focused on cognitive processes of driver. So all kinds of modeling about cognitive and behavior modeling. So I wanted to make new protocol about emotion and driving research. So to do that, we need to understand, right, whether they are in affective states or in emotional states. So we utilize a bunch of different monitoring sensors. We do neuroergonomic devices, so fNIRS and EEG, and we do eye tracking and facial affect detection system and ECG for heart rate. And from the driving simulators, we can get all the driving data. So that's how we work. And in terms of research protocol or a procedure, we have them induce their own emotions. So we have used a bunch of different technologies or techniques. So we have them watch movies and listen to music or read some passages, but the most effective way is have them write their past experiences about specific emotions. So that's validated the most, and strongest induction mechanism. So we do that and then have them drive. And surprisingly, they drive really bad. And then after that, we do some interventions using sound or listening to music. And we put the voice agent or robot agent, and then they develop some conversations so we can help out regulate the emotion or mitigate the emotion effects on driving. So that's how we work here. And this is just, one of my previous PhD students' dissertation. We've done, more than 20, 30 studies here, emotion driving, but this is kind of very interesting outcome. So I always use this as an example. So she had three different groups, conditions. So the first group, neutral, without music. So they drive without emotional induction and without music. And then anger group, so they induced emotion anger, and then they drive that they listen to music while they're driving. The third group, they also induced anger, but they didn't listen to music. So you see the first two groups, HR meaning heart rate pattern very similar, right? And the only third group, anger without music, shows significantly higher heart rate, right? And this is the results from the fNIRS. So fNIRS is basically very same as fMRI, and then we monitor the prefrontal lobe and oxygen level, which is activation. So even though you don't understand this fNIR data, but you just see the pattern. So the first two groups very similar as this HR human the heart rate results, right? But only the third group, anger without music, they show different pattern. So the take home message: when you're angry, turn on the music. So that's the title of her paper. All right, then that's kind of psychological experiment using driving simulator and then music, right? But also we do computational modeling. So this is different levels of approach. So I'm in ISC and IS people all love math and optimization. So we do simulation and then computational modeling. So this is an example of using QNMHP, Queuing Network Model Human Processor. So this is one of the cognitive architecture framework which we can do build a computational model based on. So after getting all the psychological data, we have all the numbers, right? How long it takes for each cognitive processes. So we do that math, then we can predict driver responses or behavior when we change the parameters about the display or interface. So based on their the different types of interface parameters, we can predict their driving behaviors. So that was very successful, and we published some papers out of this Q&A MHP application. Then now, until now, you heard about psychological experiment and cognitive modeling. So you're probably curious about, okay, where is engineering, right? Where is application? And this is the application. So one of my PhD students, he created the real-time driving performance-based sonification. So I play that sound, and hopefully, do you hear some sound and do you see the?
Yeah, we can hear.
Okay, great. So you see here, it's Steven's foot, and do pedaling, gas and brake pedaling, and then steering wheel. So he's basically driving the simulator, but you also hear the sound, right? So what he did is he made another the middleware. So extracting all the driving simulation data in real time. And then he made a mapping between this driving data, which is numbers, right, with musical parameters. So he's actually driving, but he's playing instruments with this steering wheel and then pedal. So where we can utilize this type of sonification application. So depending on the mapping, the sound can reflect how you're driving, right? So if you hear some good music, then oh, I'm driving very well. But depending on how we make a mapping, right, we can do inverse mapping. And if you driving very bad, then you can hear all kinds of cacophonous soundscape, or we can even make some warning sound, right? So that's where we can utilize this type of in-vehicle sonification. So based on all these, design and creative music making, we did some research project with Hyundai Motors, so the industry partners, and then this is one of the project we've done and the concept video.
Vehicle automation technology is increasing. In the past, drivers were in charge of the driving tasks. In the future, we predict that Level 4 automated vehicles will take care of a majority of the driving tasks. However, with the increase in automation will come new non-driving tasks, and these tasks will require new auditory displays. We had three goals for this project: to design auditory displays for new use cases, to explore the design space of Level 4 vehicles, and to test these displays in empirical research. There were four main phases: literature review, sound design, focus group evaluation, and a driving simulator study with motion-based platform. For our sound design, a team of 5 designers developed earcons and speech alerts for 7 relevant use cases in Level 4 vehicles. Earcons are a brief and abstract sound that conveys meaning. Here is a sample earcon. In an online focus group, we evaluated our sound design through conducting 3 focus groups with 12 participants. In our simulator experiment, we used a motion-based driving simulator to test our proposed displays with 3 conditions: visual only, visual with earcons, visual with speech, for 20 participants. Participants preferred natural sounds and harmonious sounds for earcons, impersonal messages for speech, and overall all cases were deemed useful. Overall, our sounds reduced perceived workload, especially earcons, increased situational awareness, and increased trust in the driving simulator. In conclusion, the sounds we designed were effective tools in increasing situational awareness, improving trust, while still delivering the desired user experience.
All right. So we've done, this type of, sound project with industry partners and for DOT and a lot. And we use speech, voice agent, and warnings and bips and bops. And the take-home message from this project is just adding simple non-speech sound. So when we call ear con, that's just arbitrary musical sound, and that surprisingly increased situational awareness and trust. So towards the automated vehicle. So that's actually great. So we wanted to monitor both driver states and driving performance to understand better about the driving scene. And then, interestingly, the emotion as a construct that's different than traditional construct like a workload. So those are two different concepts. We found that, and by all means, we designed all kinds of auditory displays and sonifications, and that worked and facilitated safer and better user experience. So we do a lot of different driving projects. Of course, I'm not able to present everything, but we've done more than 10 experiments about sonically enhanced gesture interaction in the vehicle. And you see here, they do some gestures. And then nowadays, we do a lot of research with in-vehicle agent and powered by LLM. So we used ChatGPT and Llama and how that real-time conversation can help out drivers. And of course, we're still working with FRA and DOT and industry partners and design auditory warnings and multimodal warnings. Okay, now that's driving project, and we move on to the assistive robot project. So the first one is about designing interactive musical robot for children with autism, and we wanted to intervene, help out their social interactions. Then why we interested in social interaction? Because that's really by definition, children with autism, they have difficulties in terms of social interaction, and emotion is the core concept of that social interaction with other people. That's why we wanted to intervene that. And then why do we want to use robots? So literature shows people with autism, they prefer interacting with animals, computers, and robots compared to human. That's because we believe those entities simpler to interact and fewer cues than human, and also we can predict more easily. That's why they want to interact with robots. And then why music? Because music is inherently emotional. So we wanted to utilize music and physical activities so we can promote their social interactions. So again, we developed a bunch of technologies monitoring their faces and behavior, motion, and also we developed some interfaces. We can have their communication better in terms of motion to sound and other types of technologies. In this line of research, we started doing the robot acceptance research, so what type of robot they prefer, and also we designed a bunch of different emotional cues, facial of robots, and gesture of the robots, and speech, and even non-speech like uh, non-semantic utterances. So that was kind of very interesting research. And then we did some experiment with people. So this is another concept video about this project, and hopefully you can hear the sound. It's a little softer.
Human communication is very complex. It consists of words, facial expressions, and body language. It not only involves informational contexts, but also emotional flows. For children with autism, emotions can be a mystery. Not only do they experience trouble understanding the emotions of others, children with autism often have trouble expressing their own emotions. Our goal in this project is to touch on this aspect, making that understanding a little easier, combining robotics and musical activities. Meet Romo and Darwin Mini. These two robots will interact with the child and with their surroundings. Romo can present many facial expressions, while Darwin Mini expresses himself through body language and gestures. The robots can express a wide range of emotions, such as happiness, sadness, and frustration, according to dynamic social cues. Children with autism experience their surroundings at a higher intensity than we do. Lights may seem brighter or sounds may seem louder. For our pilot study, Romo and Minnie will both go through a maze-like scenario. Here, they encounter objects that stimulate each of the 5 senses. The child observes the robot's reactions at physically partitioned stations. By watching how these robots react to the obstacles in the maze, the children will build a sense of empathy with the robot and will also learn how they can avoid or overcome sensory overload of their own in the future. Studies show that there's a strong correlation between the neural domains for music, emotion, and motor behaviors. Studies also show using robotic therapies for autistic children was very promising. We believe that by combining robotics and musical interaction, we can promote development in children's emotion and social interaction. Along with scenarios that engage the robot's 5 senses, we will also create sessions for the robot to react to music and to the reactions of the children. Different songs will evoke different reactions, and different reactions of the children will also generate new robotic actions. Therapy with other people can produce a sensory overload for children with autism. By using robotic therapy, the children will learn while still feeling that they are in a safe environment. Robots can be predictable and, in some sense, more friendly and approachable than adults. We look forward to introducing our robots to more students.
All right, great. And we've done a bunch of different experiments with this type of robots and with kids. And one of my CS students, she wrote her master's thesis about this dance freeze game with robot dancer and human dancer. And if you see here, it's very interesting. So we hypothesized, anyways, kids are kids, so they all love robots. But very interestingly, if you see here, so these 3 are independent autistic children, and the last one, the blue bar, is the average of neurotypical kids. So as you see here, this autistic kids significantly higher interaction level compared to neurotypical kids. So they prefer dance with robot dancer. But all other neurotypical kids, they actually prefer interacting with human dancer. So our hypothesis was wrong, and which is very interesting. All right, so we wanted to learn about different things because that was like 10 years ago. I did this research and learn about different robots. So they preferred humanoid robots and animoid robot compared to fantastic robot or mechanical robots. And interestingly, both when appearance and the speech style more humanoid, right, or humanized, anthropomorphic, they actually thought or considered robot as their companion. And then by all means, music worked, induced more of their behavior and motions. And obviously we learned, there should be some robot learning, right? It's not just one way. So robot also has to learn individual so that we can create more personalized innovation. And then based on this robot project, working with autistic kids, I had an idea. So, we probably utilize this, robot program for neurotypical kids as well. So what about we apply this into STEM education, or we can create STEAM education. So STEAM meaning STEM plus art and design. So we developed new projects. So now based on this, project with kids with autism, we developed more autism projects. And now in my lab, we have 4 or 5 different autism projects, mostly with robots, but for autistic adults, because they also have all kinds of problems, right? They have to be independent. So we have different projects for autistic adults. And like I said, we developed this program for neurotypical kids as well, and created STEAM education. So I just got a new NSF funding about this STEAM education program using robots we call robot theater. So I'll play a small video about this robot theater program.
The Child Robot Theater After School program promotes STEAM education using various AI tools and robots. The primary goal of this program is to explore young learners' perspectives of AI robot ethical implications, as there are only a few research studies conducted regarding this issue in early education. 30 elementary school students participated in this pre-test and post-test within subject study. We conducted children's surveys and interviews before and after our program to investigate the program's impact on children's interest in STEAM, perception and trust of AI and robots, and their perspectives regarding the 5 ethical items: fairness, transparency, non-maleficence, privacy, and responsibility. This 9-week program consists of 4 modules that facilitate STEAM learning in a creative and innovative way. In each module, we provided lectures and hands-on activities for children to learn about STEAM-related materials. 6 robots and a few AI tools, such as AI Duet and Microsoft Image Creator, were involved in this robot theater program to demonstrate materials. In particular, Now was a teacher assistant to engage students learning in the classroom.
Hello everyone, my name is Now. I will be your robot instructor for this after-school program. You will learn different aspects about robots. You will enjoy your human-robot interaction experience here.
Another unique thing about our program is that we program robots to act, and we created 4 short videos addressing macro and micro ethical topics. Each video was played at the end of each module to facilitate students' discussion regarding those ethical issues.
Is it also important to treat robots the same way you want to be treated?
Yeah.
Yeah. Why or why not?
Because robots will be nice to you.
By providing this unique learning opportunity with AI tools and robots, we hope that the outcomes of the present study will bridge the research gap in AI robot ethics in early education and prepare the young generation for the coexistence of human and advanced technologies in the future.
All right, so that's about robot projects, and we move on to the last chunk. So it's really about art. So what we do with art, and I'm going to start with the developing the platform we call immersive, interactive, and sonification platforms. So we do this for dancers and performing artists, and we wanted to create some platforms so artists and dancers they can do some experiments. So again, we have a bunch of different monitoring tools, and one of them is cameras. So at Michigan Tech, I used to use Vicon and cameras, and we monitors dancers' movements and motions, and then we created this type of visualization and sonification based on their motion and location. So to make this type of project, we created preliminary technologies and system configuration. Again, accessible interfaces. So lay people or dancers, they can also make a mapping between their motion and then sound and visuals, how they can create different things. And we've done a bunch of workshops with local dancers. So this is the first iteration we did. I did this in 2012. So 13 years ago. So my student, a W student, Mike, he has an anklet here using Velcro tape, and then we had a camera, and then he plays a piano on the floor.
Record.
There you go.
So those red dots are all cameras. So I don't know how many of you have seen this, but have you watched the movie Big? Then where Tom Hanks was cast, and he actually plays piano on the floor, and this is omazu for that movie. All right, and then we invited Tony Orico, the performing artist, and he's rolling with graphite in his hand and then making this type of gigantic geometric pictures, and we have them have all the sensors and then drawing on the floor. So this is kind of what he was drawing on the floor with us, and this is another drawing. So he's rotating with this graphite and then making these works on the floor, and then we superimposed these two on the digital version because he has all the sensors while he's making his painting that also projected on the display wall. And then we have him wear the physio sensors, so respiration and heart rate, got all that sensor time, and we created sonification based on that, and then we exhibited that in the art gallery in Houghton, Michigan. So based on all this type of trial and error, my PhD student, he did his PhD dissertation about dancer sonification. So the difference is dancers make their choreography based on their music choice, right? But in my lab, dancers actually make choreography that makes music and sound and visual. So it's kind of reverse engineering. So this is kind of dancing angry. So she's creating angry sound. And then this is example of tender. Okay. So we wanted to create multi-dimensional artwork, expand that perceptual dimensions, which is the original definition of aesthetics. And so we can change this representation model of art, like static painting, right, into performative model of art. So more dynamic because I'm doing sound, right? I'm a sound designer. So I always want to add temporal dimension to the art. So even though it's a sculpture or a painting, we want to add time dimension. And then we do a bunch of design research with artists. And then all this technology actually can help when they ask, what is art? How can we change the art? That's the definition of art. So that's what we always ask in contemporary art. So I'm mostly done, and then give you a couple of more examples so you can enjoy the remaining time, and then we can get into the Q&A session. So this is painting sonification. So we analyze all the painting colors and contrast using the computer vision, and then we make a mapping with musical parameter. So I'll play two different sound, and then that sound actually came from the painting itself. So you can guess which sound is for which painting. So this is the first sound, sonification. And then this is the second sonification. Oh, that's interesting. So you're not able to hear the sound. Okay, I see. Okay, sorry for that. If you're not able to hear the sound, then yeah, I can just move on. So we again created, different VR technology like handheld tablet as a window to the room scale virtual reality. So we created sculpture. So we collaborate with Zach Doran Sova. So he created a ballerina sculpture, and we also made a digital replica here in the handheld virtual reality. And then when audiences, interact with each other, they can see this actual sculpture, but also virtual sculpture here. And then depending on the interaction between audience members, the sculpture actually can morphing and also changing the size. So that's kind of interesting project. if we're not able to hear the sound, then maybe let's try whether you can hear the sound here.
Hi, today I want to share a project with
Can you hear that?
audio-visual augmented reality, enhancing visual art experiences through sonification and visualization. In this study, we explore how it would transform the way we experience art, making it more engaging, emotional, and immersive. These are the 8 paintings we're using. We designed a 2x2 within subjects experiment. Participants view 8 paintings under 4 different conditions, with or without audio augmentation, and with or without visual augmentation. They will experience all combinations during the study. To create the visual augmentation, we used the HoloLens enhanced with image tracking, 3D elements, and background panels, while keeping the central artwork untouched to maintain its original impact. Here's an example, Woman with a Parasol by Monet. We recreate a vibrant and dreamy atmosphere. Guernica by Picasso, representing abstract and surrealist art. We brought it to life by turning elements into 3D models and layering a soundscape that evokes its unsettling surreal tone. This study shows how technology can deepen our connection to art. By combining sonification and AR, we hope to enrich museum visits, improve art education, and inspire new ways of storytelling through visual culture. Thank you so
All right.
much for watching.
Then we move on. Okay, so the last slide. So as you see, embodied interaction serves as foundation of aesthetic computing, and this body movements, which the artists and dancers have expertise on, right? These body movements function as a new representation of computing, so we can promote more accessible and personalized computing environments. All right, so I'll stop here and then I can get any questions.